I'm Martin Rowe with EE World. I'm here at APEC 2025 in the Keysight booth. This is Heidi Barnes from Keysight, and Heidi is an expert in power integrity. And what we have here is a simulation of crosstalk and
ground bounce.
Ground bounce. Okay. Heidi, why don't you tell us about this new test equipment that you have?
Okay, well I'll have a few slides here to show you what we're talking about. There's a lot of people asking what's the difference between crosstalk and ground bounce. Well, we have a demo board to explain that. This board has a load, a dynamic load, FPGA type device, and you can see here we're showing you the aggressor power rail that's powering 3/4 of that device. We have a victim power rail, the quiet power rail, that's on 1/4 of that BGA. What's very interesting with our simulator is we add in, it's all done automatically, is a reference ground, just like in CISPR conducted EMI measurements. We have a ground reference, ground plate in our EM simulation. We have a dynamic sink that we can put in there, a dynamic load, and we're also getting measurements on this board to do the same thing. So let me explain a little bit better. We're turning the load 50 amps on and 50 amps off. When we turn that 50 amps off, we actually see a lot of noise on our power rail. So
yes, we do.
You can see that voltage rail. But if you look at the victim, we're also seeing noise, okay? But we don't know, is that coming from net-to-net coupling, crosstalk, or is it coming from ground bounce? What our tool lets us do is actually separate it out. So up here you can see net-to-net crosstalk, and we can see what's happening on our aggressor power rail versus our victim power net in blue. We see a little bit of coupling there. We can also put ripple probe points, put probes on the ground in different locations and look at what the noise is on the ground. And so what that lets us do is actually plot at a location, at a device, we can actually look at what's the noise on that power net versus the noise on the ground net, and that helps us troubleshoot where is the noise coming from. And that's exactly what I'm showing here with our current, this is a PCB EM simulation, the same board I was just showing. This bottom board is the, bottom layer here is the aggressor net, and then you can see the victim net is not attached, but you can actually see when you go here, you can actually see the crosstalk onto this victim net. So the victim net here, and it's interesting to me is a lot of the coupling happens at corners. So that's a high radiation or coupling point, is when you have a sharp corner.
So what we're looking at, these colors are showing electromagnetic radiation. They're not showing temperature.
It's showing the current density. So from the EM simulation of the electromagnetic fields, we can actually look at the current densities. So we have 4-phase VRM, 50 amps of current coming into this FPGA, and we're looking at what crosstalks into our victim net.
So how does
it? So this is a crosstalk right here.
So what's the coupling path from the source to the victim?
So just a net to net. It's just EMI. It's conducted EMI, you'd basically say. Or not conducted. It's radiated EMI.
Radiated. I was going to say, when you look at those switching signals on and off, and especially when you see that bounce, that's radiated emission right there, or conducted emission.
And I have to say, a lot of times when I say it's radiated, it's because of the common mode. The current's going in the same direction. Right. And so then you get that radiated EMI.
Yes, that's what keeps a lot of EMI engineers in business.
Yes, definitely. But I think it's been difficult to simulate, so that's why I'm very excited. Most of the time, to try to set up this sort of differential excitation and look at ground noise versus power rail net-to-net coupling, it takes hours and days to try to figure out how to set that up, get boundary conditions, mesh settings, port settings, and this is all automated for you. So it's very easy.
All right, Heidi, thank you very much.
Okay, thank you.